Hey everybody, today I'm going to talk about a new training technique that I developed for GAN, and I think it's pretty cool. It gives really nice results and I hope you will like it. So a little bit of introduction. Modern GAN architectures are well known today for producing high quality, diverse images. In recent years, there are many attempts to try and control their output in a way that is intuitive for humans. In a case of generated human faces, that means being able to change features such as hair color, gender, expression, and more, without affecting the other features. On first glance, it seems impossible. The latent space of GANs, that is the vector that is used as input for the generator and controls the resulting face, it has no reason to encode features that are intuitive for humans. And even if it did, we had to manually go over each element in the latent vector to check if it controls a feature we have interest in. Another issue that might arise is that some features might be correlated, while we want each to be able to change independently and still create a reasonable image. To overcome this challenge, I thought about using PCA, which discovers the highest variation, zero correlation features in the data. If you want a video explaining it in depth, leave a comment to let me know, but for now, it's enough to know that it's a dimensionality reduction technique that finds new access for the data that allows high quality representation of the data on lower dimension. Some time ago, I watched a video by CodeParade where he combined PCA with autoencoder, which is another kind of image generation model to get control of the generated images. But the issue with autoencoders compared to GANs is that they produce an image that's kind of blurry. And that got me thinking, maybe I can combine the explanation power of PCA not with an autoencoder, which will give blurry images, but with GANs, that gives very crisp, bright, clear images. After lots of experimentation, I managed to combine PCA into the training process of GANs. To begin with, I started with LabML's StyleGAN2 implementation. It's very well written, and if you want to learn the StyleGAN2 model, I recommend starting there. I'll put a link in the description. Anyway, I decided to convert their implementation into a vanilla style GAN with latent vector in the beginning only, instead as an input to every block in the generator as usually is done with StyleGAN2. The training process that worked best for me is as follows. To create the latent vector that I'll feed to the generator, I applied the PCA to the batch of real images that will end up as input to the discriminator. The latent vectors were used by the generator to create fake images. Then I applied PCA to the fake images as well, and took the L2 loss between the latent code of the real images and latent code of the generated images. That loss was added to the regular loss of the generator. And if you want to know more about it, check the vid right now. Anyway, by doing that, I asked the generator to accomplish two goals: to create images that are indistinguishable from real ones, and make sure they have the same features as the real images. Mind you, I also tested achieving this without PCA, just with minimizing the L2 distance between the real and fake images themselves, as in pixel compared to pixel. But that didn't work well, and that's because it was too crude of a comparison. I don't care about each pixel, I just want the underlying features of the image to be similar: hair color, face orientation, and such. By combining PCA in the training process, I managed to achieve two more benefits besides controllability. By forcing the output image to mimic the real ones, I forced the generator to stretch the distribution of the generated images to match the real ones, which leads to better diversity. On top of that, one of the issues for GANs is that the latent space is not well conditioned. That means that a very small change in the latent code can create a substantial change in the output image. Styled GAN 2 solves this by using what's called path length penalty loss, but from looking at the way the images change as the code change, I think PCA training helps with this as well. Another important training detail is that training is much more stable when we start with only GAN loss and set the PCA loss coefficient to 0, and then linearly raise it as training continues. Of course, making the generator trying to match the true distribution of images is a big task, while also asking it to make images that are perfectly realistic. No model can accurately 100% mimic reality, so compromises must be made. The model will either not make a perfect reconstruction of the original image's features, or won't make realistic faces. I wanted it to prioritize realism, so at the last part of the training, I started to linearly decrease the coefficient of the PCA loss, sort of relaxing this requirement and letting the generator focus on fooling the discriminator. The results are fun to play with. I created a small widget to play with the model. Let me show you how it works, and you can go to my GitHub, link in the description, download the notebook, train a model on a dataset of your choice, and play with it yourself. The widget is in the end of the notebook. Change this image using these 7 sliders. Each controls a different feature. You can say a different principal component from the PCA process. So let's go over them and see if we can describe verbally what they are doing. So the first one, it seems like it has to do with the background, and it can make it darker or brighter. The second one, let's see. It controls the direction of the light from the right or from the left. How about this fourth one? Seems like it controls either age or amount of hair, or both of them. And from trying that before the video, I know that the 17th feature, which is controlled by this slider, is actually the gender. So I can make it sort of more manly or more feminine, right? As much as I want, which is pretty cool, I think. So feel free to download the notebook from my GitHub, train a model on whatever dataset you want, and in the left cell you will find this widget to play with your model and see what kind of awesome creative images you can come up with by combining different values for different features. And that's it. Thank you so much for listening, and if you would like to be noticed when I'm releasing new videos, feel free to subscribe. Again, thank you, goodbye.